everyone, welcome to GemChem. Now today's video is on alkenes part 6 video, and here we will deal with the chemical properties of alkenes. So first chemical property which we are going to deal with is hydrogenation of alkenes and also about heat of hydrogenation. Now before starting, if you have not watched the previous videos on alkenes where we have dealt with method of preparation, you can watch it. I will give the link in the description box as well as the I button present above this video. Now let us start today's video. Now what is hydrogenation? Alkene is treated with hydrogen in presence of catalysts such as nickel, palladium, platinum, etc. to give alkene. And this is the alkene. So on adding hydrogen it becomes an alkane. Commonly ranitidine used as catalyst. Catalyst absorbs hydrogen on the surface of it where the reaction proceeds. Catalyst decreases energy of activation of hydrogenation also. Now we will see the mechanism. So for mechanism we first take a catalyst surface. This is a catalyst surface, and first function is that hydrogen gets absorbed into this. So we finally get a structure of catalyst surface with hydrogen atoms attached to it. Right. Now we see a alkane molecule comes into the play to get attached to this catalyst surface. Not exactly to the catalyst surface, but it gets attached to the hydrogen present on it. So if this is the catalyst surface, the bond with the hydrogen breaks up and the bond formation with the alkene starts. Now ultimately what happens? This gets detached and we get this product with hydrogens from the catalyst surface, and the catalyst surface remains with the other hydrogens present in it. Right. So what we can see, that the attack of the hydrogen takes place from the same side of the alkene. So we can tell that there is a cis addition, or rather specifically it is known as syn addition. That is syn addition or cis addition. So this is important. Now we will see an example. Now see this one. This is an alkene, this portion. Now when hydrogen catalyst gets added, so the hydrogen comes from the downside, that is from the same side. So this proves a syn addition. Now we will deal with heat of hydrogenation. Now basically for getting the heat of hydrogenation, we need to know the energies of the bond which will be formed and which will be broken. So first of all we see that this carbon-carbon double bond gets broken and hydrogen-hydrogen single bond gets broken. Whereas this carbon-hydrogen bond and this one is formed, as well as this carbon-carbon bond remains intact. So we take the bond energies and write them. For carbon-carbon double bond it is 145 kilocalorie per mole. For hydrogen-hydrogen single bond it is 103 kilocalorie per mole. And for this, since there is a bond formation, there is release of energy, so the energy will be negative. So for this carbon-carbon single bond it is minus 83 kilocalorie per mole, and for this carbon-hydrogen, one carbon-hydrogen bond formation, it is minus 99 kilocalorie per mole. Now we see what? The total energy. We will see the total energy. So 145 plus 103 gets this value, that is 248 kilocalorie per mole. Similarly for this one, that is for the product, it is minus 83 kilocalorie per mole plus minus 99 into 2, because there is 2 carbon hydrogen bond formation, and ultimately we get the value to be as minus 281 kilocalorie per mole. And what we do? We basically deduct the value. So what we get? We get it as final plus initial. So we get our heat of hydrogenation, which is given by delta H as minus 33 kilocalorie per mole. Now this delta H is known as heat of hydrogenation, and often only magnitude is supplied. Obviously for hydrogenation, we have to have some energy profile diagram. So what is the energy profile diagram? This is the energy profile diagram. So this is the alkene part with the hydrogen, and it goes down to form an alkane which is more stable than alkene. So this part, this difference is the magnitude of delta H. Now what it states? It states that lower the magnitude of delta H of, that is, heat of hydrogenation, more stable the alkene, provided of course the stability of alkenes are approximately same. So this statement is highly important. So you have to keep in mind, and we will see this application. Now see, these are the three reactions. So first we name them. Previously also we have seen how to name the alkenes. So if you have not watched the IUPAC nomenclature for alkenes, you can watch it. I will give the link in the description box as well as the I button present above this video. Now let us start to name it. So this will be butene. Since it is in first position, no need to write the name. Here the double bond is in second position, so we will write cis 2-butene, or we can write cis but-2-ene, and this is trans 2-butene, right? Now see, here heat of hydrogenation, here it is minus 30.3 kilocalorie per mole. It decreases, that is minus 28.6 kilocalorie per mole, and here it is minus 27.6 kilocalorie per mole. We have already seen in the previous slide that is lower the magnitude of delta H, more stable is the alkene. So from here what we can conclude? What are the conclusions? This is important. First conclusion is more substituted alkene is more stable. We are seeing that 2-butene is more stable. So more substituted alkene is more stable. Another factor from trans and cis, we are seeing that, what is another thing? Trans alkene is more stable than cis alkene. So trans alkene is more stable than cis alkene. So these are the two conclusions or applications which we can draw from the heat of hydrogenation, right? From these three datas. So ultimately what we can write? Then we will justify our statements. First we can write that suppose this is tetra substituted one. So this one will be more stable. Then comes our tri-substituted one, which will be little less stable than this one, first one. Next comes to be our di-substituted one. Then comes our this one, that is di-substituted cis one. Okay, this is one, and then it is this one, the single substituted. Okay, now what we see here, as we go down, stability decreases, right? And another thing, magnitude of delta H increase. So this is important. And another factor which we have drawn previously is that trans alkene is more stable than cis alkene. So why is it so? Let us justify the first line. First line is justified because we know hyperconjugation, right? So if it is more substituted, then the hyperconjugative hydrogens will also increase. So the stability is justified. So this stability is justified using hyperconjugation. Okay. And the cis and trans case, we can easily say that in cis alkene, crowding between the two alkyl groups, that is in this case, is more. Thus its stability decreases. and in transalkene these two CH3 are far apart, so its steric crowding decreases. So we can justify that transalkene is more stable than cisalkene. But remember one thing very carefully, this heat of combustion or heat of hydrogenation is not a concluding property for the stability of alkenes, because the final product is alkenes and the whole process depends on stability of alkenes also. So the both things matters, alkenes as well as alkenes. So this gives little idea, not complete idea about the stability of alkenes. So this much for today. Thank you for watching. Do not forget to like, share, subscribe and comment.